Hello, my name is Harmish Bhatt, and I'm applying to be a ULA for Chem 261. So, just a fun fact about me is I have a black belt in Taekwondo. I do miss that a lot, but um, to me, I think Orgo is a really fun, just big puzzle, and I think a lot of students have been misconstrued to just do practice problems, and they think that that will solve the puzzle, but I think it's really important that they're taught all the concepts before they do those problems very clearly, so and they have a good understanding of that, so they can apply each piece where it belongs. So here I'm teaching a problem on substitution versus elimination reactions. Here we have a 3' alkyl halide, and we're going to see what types of reactions can occur first just in general, and then here with this N triple bonded carbon nucleophile. So first, let's start with SN1. So can SN1 occur here? And the answer is yes, because we have a carbocation that will form in SN1, that is our rate determining step. And since we have a 3' alkyl halide, all these substituents will stabilize the carbocation. The same goes for E1, except the other factor we look for in E1 is beta hydrogen. If we have beta hydrogens, then only can we do elimination reactions, since they need to be taken off in order for alkene to bond. So here, E1 can occur. The only condition for E2 is also these beta hydrogens being present. So we'll say, yeah, that can occur as well. Now, SN2 actually will not occur here due to the amount of steric strain that comes from all three of these substituents on the substrate. The nucleophile will struggle to attack due to all the strain being caused here. So now we're going to predict the reactions that will occur for this specific molecule, this N triple bonded carbon. And here, first off, let's think about basicity. We know that the pK for this molecule is 9, just something we were told in class to memorize. And the rule for our class is only a pK greater than 14 is a strong base, since this is a generally stronger acid, and therefore the conjugate base will be weaker. So here we have a weak base. And we have a good nucleophile because there's a charge, which means that it would like to attract, or it would like to attack an electrophile. So here, good nuke, weak base. So first off, we can immediately get rid of E2 here, since we have a weak base, since the rate determining step involves the nucleophilic attack, which is really strong. It's really hard to perform. Sorry, the deprotonation, which is hard to perform with a weak base. Now, let's look between SN1 and E1. And E1 generally won't occur over SN1 due to the fact that we do have a good nucleophile, and therefore we will go with this. And we'll also say that no reaction can occur, and we'll look at that once we look at the solvents here. So here we have a polar protic solvent. So what can a protic solvent do? It can stabilize transition state and carbocations, which will form with SN1 due to its H bonding properties and dipole interactions. So polar protic will result in SN1. But if we have a polar aprotic solvent, then that transition state, that intermediate, the products, nothing will end up being stabilized. It will be a highly unstable reaction, so we'll actually have no reaction here.